So you can see that you're told you should have a cutoff frequency of 100 hertz, and then you can go ahead and calculate what the value of that resistor should be. And the way this will work, you're going to be measuring the voltage on both sides. If you have a steady state DC voltage, the capacitor is acting like an open circuit. In other words, like this doesn't even exist. Once it reaches the voltage, then you won't have any current across here, or essentially no current. So you'd have the same voltage on both inputs to the oscilloscope. And then what happens if you add in some some high frequency noise here, as that voltage spikes up, you'll see the spike here. But what happens, of course, is the capacitor, you can't have a sudden change in voltage, right? You'll start having some current flowing through into it, and the voltage will gradually come up, and then if the voltage drops down, it will gradually discharge. So the idea is that this smooths out the noise and takes out the noise. So this is a good way to reduce the noise, but it's not perfect. In other words, here's your cutoff frequency right here, and you have basically the output of the circuit is decreased by 3 decibels. So it's basically like a half power point. And as the frequency increases, so here's your low pass where basically there's no reduction in power. And then obviously the higher the frequency, that gets rid of a greater percentage of it. There's a couple of things to be careful of here. And one of them is you'll notice that this is the rails on the op amp are set to -5 volts and 5 volts. So here's the problem. If you're trying to measure a low voltage, you may remember from the slides in class, so here's your ideal op amp where you can go right up to the rails, right? The voltage that's being supplied to power the op amp. You have this region where this equation, once it's saturated one way or the other, you're right at the rails. But in reality, you can't get all the way there. So in this case, there's, say there could be a 0.5 voltage. So this is, instead of going from, if this was -3 to 3, I'm sorry, if this was -5 to 5, then you're really only able to get to -4.5 and up to 4.5 over here. Or in the case if you had one side connected to ground, so now maybe you can only get from 0.5 to 4.5, right? You can't, once you get down to here, you can't get any lower than that. So that means that we have low voltages, then coming in here, even with the gain, it's still going to be pretty low. And so we actually have to have a negative voltage. And the TAs and SAs can show you how to use the hook up the power supplies so that you can actually have -5 volts to +5 volts on the rails. So once you have this set up, you will have a sample set up in the lab to show you how to have the lever arm and this bracket, a wooden bracket that the motor attaches to. So now at these different powers, you can quickly measure the current sense voltage, and from there determine how much current is going through the motor, and then you'll be able to record that. Right, so you'll measure the current sense output, and then from there you can calculate. You have to, of course, divide by the gain to get the actual voltage across the 0.5 ohm resistor, and then you'll be able to calculate the current, and you'll have the force from the scale, and you'll be able to then calculate the torque and graph current versus torque. And the last few parts here, you'll just, first of all, just using the Arduino loop, do a digital writes to turn the voltage on and off basically. And I think this part's pretty straightforward. In this part here, you'll actually, inside the loop, you'll have a while one statement. So you should write about whether you expect what to happen there. And in this last part, you'll include an analog read and a digital read. So I think that's pretty straightforward, and I hope you have a great time doing this lab.